For more than 3 decades, space telescopes have transformed the way humanity sees the universe. Hubble revealed breathtaking galaxies, while the James Webb Space Telescope pushed our vision deeper into cosmic history than ever before. Its images showed some of the earliest galaxies formed after the Big Bang, making many people wonder if astronomy had finally reached its ultimate tool. But NASA's next great observatory is designed with a completely different purpose. Instead of focusing on tiny regions of the sky in incredible detail, it will scan enormous portions of the universe at remarkable speed. Its mission isn't simply to capture beautiful pictures. It's to answer some of the biggest questions in modern physics. This is the Nancy Grace Roman Space Telescope. At first glance, Roman may not seem revolutionary. Its primary mirror measures 2.4 meters across, similar in size to Hubble's and much smaller than James Webb's 6.5 meters mirror. If mirror size were the only measure of performance, it might appear less powerful. But astronomy isn't only about seeing deeper. Sometimes the greatest discoveries come from seeing wider. Roman's greatest strength is its enormous field of view. In a single observation, it can capture an area of sky roughly 100 times larger than James Webb can observe at once. That means Roman can survey huge regions of space in a fraction of the time required by previous space telescopes. Think of it this way. James Webb is like an incredibly powerful microscope capable of examining one extraordinary object in astonishing detail. Roman is more like an orbiting survey aircraft, photographing an entire landscape before scientists decide where to look closer. These two approaches complement one another perfectly. Modern cosmology faces questions that cannot be answered by studying one galaxy at a time. To understand how the universe evolved, scientists must examine millions, eventually billions, of galaxies spread across enormous distances. Only then can hidden patterns begin to emerge. One of Roman's primary goals is investigating two of the greatest mysteries in astronomy: dark matter and dark energy. Everything we can directly observe, stars, planets, gas clouds, black holes and galaxies, accounts for only a small fraction of the universe's total energy and matter content. The remainder appears to consist of invisible components that scientists call dark matter and dark energy. Dark matter cannot be seen directly because it neither emits nor reflects light. Yet astronomers know something unseen exists because galaxies rotate far faster than visible matter alone can explain. Without additional gravitational influence, many galaxies would simply fly apart. Dark energy presents an even greater puzzle. Observations show that the expansion of the universe is accelerating rather than slowing down. Something appears to be driving space itself to expand faster over time. Scientists can measure these effects remarkably well. What they still don't know is exactly what causes them. Roman was specifically designed to collect the enormous amounts of data needed to investigate these questions with unprecedented precision. One of its most important techniques relies on Einstein's theory of general relativity. According to Einstein, massive objects bend spacetime, causing light traveling through the universe to follow curved paths. This phenomenon, known as gravitational lensing, allows astronomers to detect invisible matter by observing how it distorts the appearance of distant galaxies. The distortions are incredibly small. Looking at just a few galaxies reveals almost nothing. But when billions of galaxies are measured together, the tiny distortions combine into detailed maps showing where dark matter is concentrated throughout the universe. That is exactly the kind of observation Roman was built to perform. Instead of focusing on individual objects, it will create one of the largest cosmic surveys ever attempted, providing an entirely new perspective on the large-scale structure of the universe. And this may only be the beginning. Roman's ambitious survey mission extends far beyond dark matter. The observatory will also investigate how the universe has expanded throughout billions of years of cosmic history. By studying distant galaxies and Type Ia supernovae, astronomers hope to better understand whether dark energy behaves consistently across time or whether current theories may require significant revision. Every new measurement will help improve models describing the evolution of the cosmos. But Roman's scientific potential doesn't end there. Another major objective involves searching for planets beyond our solar system. Unlike missions such as Kepler and TESS, which primarily detect planets passing in front of their stars, Roman will specialize in gravitational microlensing. Microlensing occurs when the gravity of a foreground star briefly magnifies the light from a more distant background star. If the foreground star has planets, those planets create subtle changes in the light pattern that astronomers can detect. This method is particularly sensitive to planets located farther from their stars, including worlds similar in distance to Jupiter and Saturn within our own solar system. Scientists expect Roman to discover thousands of previously unknown exoplanets, including many that other detection techniques rarely observe. These discoveries will help researchers understand how common planetary systems like our own may be throughout the Milky Way. Yet history suggests Roman's greatest discoveries may be the ones nobody anticipates. Almost every major space observatory has revealed completely unexpected phenomena. Hubble discovered surprises that reshaped astronomy. James Webb continues revealing galaxies and structures that challenge existing models of the early universe. Roman will observe the sky on an unprecedented scale, dramatically increasing the likelihood of finding rare cosmic events, unusual gravitational lenses, distant exploding stars, and perhaps entirely new categories of astronomical objects. Large surveys often uncover patterns that remain invisible when studying individual targets. By observing billions of galaxies and millions of stars, Roman will create one of the most comprehensive astronomical databases ever assembled. Instead of viewing the universe as isolated objects scattered through space, scientists will begin analyzing it as one enormous interconnected system. Hidden relationships may emerge between galaxy formation, dark matter distribution, and cosmic expansion. Perhaps the most exciting aspect of Roman's mission is how closely it will work alongside James Webb. These telescopes are not rivals. They were designed to complement each other. Roman will rapidly scan huge regions of the sky, identifying unusual objects and scientifically valuable targets. James Webb can then investigate those discoveries in extraordinary detail using its powerful infrared instruments. Roman finds the mysteries. Webb explores them. Together they create one of the most capable astronomical partnerships ever developed. One telescope provides the big picture. The other reveals the fine details. As Roman prepares to begin its mission, astronomers hope it will answer questions that have challenged science for decades. How is dark matter distributed across the universe? What is driving cosmic expansion? How common are planetary systems like our own? And what unexpected discoveries are still waiting beyond the limits of current knowledge? Every great observatory changes the way humanity understands the cosmos. Roman may do so not by looking farther than any telescope before it, but by revealing how everything in the universe fits together. Its greatest discovery may not be a single extraordinary object. It may be the hidden patterns connecting billions of them, bringing us one step closer to understanding the true architecture of the universe.